Okay, so our speaker today is Taro Sogabe from the University of Tokyo, who will talk about the reciprocal Kirchberg algebra. Please, Taro, go ahead.
Yep, thank you for introduction. And I'd like to thank the organizer for giving me the opportunity of this talk and setting for this Zoom seminar. So today, I'd like to talk about my recent work on the homotopy theory of Kirchberg algebra and the Spanier-Whitehead duality for KK groups. So first, I'd like to start with some basic introductory materials on the C-star algebras and their morphisms and KK groups. So let's start the introduction. So C-star algebra is typically non-commutative and infinite dimensional rings consisting of some linear operators acting on Hilbert space. And also, it can be understood as a non-commutative analog of topological space. For example, if we take a locally compact Hausdorff space X, then we can associate it with some C-star algebra, C of X. This is a ring of continuous functions over the space X, and this zero means the function in this ring vanishes at infinity. So in general, this ring does not have unit, but if this ring contains unit, then it means the base space is compact. This is a consequence of well-known results of Gelfand-Naimark. So this is an object in the C-star algebra theory. So next, let's see the morphisms. So in the category of topologies, usually the morphism means a continuous map from space X to Y. And in homotopy theory, people also consider another morphism, which is called homotopy set. This is a set of homotopy equivalence classes of continuous maps. On the other hand, in the category of C-star algebra, usually morphism means ring homomorphisms between two C-star algebras. More precisely, the star homomorphisms. And there is also some counterpart of this homotopy set in the category of C-star algebra, which is today called Kasparov's KK groups. So roughly speaking, the KK groups is a set of homotopy equivalence classes of star homomorphisms. In contrast to the homotopy set, this KK group always has a natural Abel group structure. And the composition of the morphism is denoted by the tensor product. Which is called Kasparov's product. So in this talk, we can understand the Kasparov KK group from this viewpoint. So next, I'd like to explain what is a K group for C-star algebra. In the homotopy theory, one of the important invariant is homotopy groups. And the ith homotopy groups of the given space Y can be given by the homotopy set. Here, this is a I-dimensional sphere. And
So sorry, you're working in the pointed category then.
yeah, so this is why use this nearly equal. So in more strictly speaking, we should take care of the base point. But in this talk, I would like to I would like to away from something like that. So from this viewpoint, the K groups can be understood as a non-commutative analog of homotopy groups. So the ith K group of C-star algebra P can be written by the KK group from I-fold tensor product of suspension to B. So since this picture is quite resembles to the picture of homotopy groups, in this talk, the audience may regard the K groups something like a homotopy groups for C-star algebra. And here, this S is some elementary C-star algebra, which is called suspension. This is a continuous function over the unit intervals, consisting of the function vanishing at the boundary. And actually, this can be understood as a function algebra over the one-dimensional sphere. So in the later of this talk, I will also talk about some notion of KK equivalence. And KK equivalence is, roughly speaking, some non-commutative analog of homotopy equivalence. But I will speak more precisely about KK equivalence later. And finally, I'd like to explain what the finitely generatedness of K group means. So roughly speaking, considering the C-star algebra P is finitely generated K groups, this is almost equal to considering a finite CW complex. So indeed, if we take a function algebra over finite CW complex, then its K groups are finitely generated. And now it is known that some nice C-star algebra or some nice C-star algebra with finitely generated K groups, then such algebra is always equivalent to some function algebra over finite or CW complex. So I want to say that the condition of finitely generatedness of the K groups is very natural condition. This is very natural condition from this viewpoint. So next, I'd like to explain about the Spanier-Whitehead duality for KK groups using kind of this picture. And also, I also give some more precise definition of the duality later. But first, I'd like to give more rough understanding of the Spanier-Whitehead duality from the C-star algebraic viewpoint. So Spanier-Whitehead duality is a duality for the category of C-star algebra, but unfortunately, not every C-star algebra satisfies this duality. So we should take some nice C-star algebra. Then there exists another C-star algebra, dA. This is called a Spanier-Whitehead dual of A. Which is characterized by the following equation. In the left-hand side of the equation, we have a so-called K homology of A. This is also given by the KK group. On the other side, we have a K group of the dual algebra. In some sense, this gives a complete characterization of the dual algebra of A. So now this is some kind of homology, and this is a kind of homology. So the Spanier-Whitehead duality is can be understood as a variant of Poincare duality, which connects the cohomological object and the homological object.
Sorry, a little question. What happens if you replace C by another sister algebra?
Another sister, yeah.
Instead of C.
Instead, so you mean, yeah, so if we put here some sister algebra B, then so this doesn't follow from this description, but follows the equation I write here follows from more precise definition of the Spanier-Whitehead duality. But anyway, this KK group is identified with the kind of this algebra. And also, this algebra can be, this KK group is equal to this one.
So if you put, if on the left hand side you put A tensor a third algebra, then this will appear on the right hand side instead of the complex numbers. That algebra would appear, right?
Yeah. So
Yeah. So I mean, make this bigger.
KKAC CV. Yeah. This second equation is also true.
Okay.
Yeah.
Okay.
So yeah, so I will also explain why kind of this equation holds by using some unit and co-unit to define which is needed to define the Spanier-Whitehead duality by more categorical formulation. So, but anyway, in this so if we put C, then the Spanier-Whitehead duality is something like a duality between the homology and cohomology. So then, next I like to explain what this nice means. So here, the nice property means the following three conditions. First one is the algebra A is separable and nuclear. So the separability is just a natural condition, which means algebra A is not so huge. And the nuclearity means this is also a natural condition, which implies A can be approximated by some elementary C-star algebra, something like a C of X or something. So they are both natural conditions in the theory of C-star algebras. The second condition is the finitely generatedness of K groups. As I said before, this condition is something similar to considering the finite CW complex. So this is also natural condition. And the third one is, this is important. This says A should satisfy the UCT. So roughly speaking, this means A can be approximated by kind of CW complex. More precisely, A satisfies some nice exact sequence to compute the KK groups. So let me explain about the UCT briefly. So in general, it is very difficult to compute the KK group by definition. Since the definition is very complicated, it is difficult to compute this object. But if A and B sits in some nice class, so-called bootstrap class, which is, in some sense, bootstrap class is something like a class of CW complex or something. But anyway, if A and B are sufficiently nice, then we have the following exact sequence. To compute the KK groups from the K groups of A and B. So this is a UCT, and in this sense, if A and B satisfies the UCT, then the K, so I said the KK equivalence is kind of homotopy equivalence, but in this sense, this is actually true. That means A and B are KK equivalent if and only if they have the same K groups. And this situation is quite resembles for the homotopy equivalence of the CW complex. That says if two space X, two CW complex X and Y are homotopy equivalent, if and only if there is a map from X to Y, and this map induces isomorphisms, homotopy groups.
Yeah, but two comments. In the X formula, don't you, is the I the same on both? Or you need I and I plus one?
I plus one, yeah. There is a degree shift by some homological reason to deal with some wrong exact sequence.
Okay, and in what you just said about the comparison with the situation for finite complexes, right?
Yeah.
You need there. You need the existence of a map from X to Y.
Yeah, this is crucial.
Whereas here
so,
you don't. Yeah.
Yeah, in the topology, this is crucial. I think so. But so. So I should mention that here we doesn't need a map from A to B. Just but in some sense, the reason why we need a map from A to B is contained in the condition A and B satisfied if you see this. So yeah, but I think they are essentially the same phenomena. So anyways, and so this is an explanation of UCT. And so in this talk, I will always consider the C-star algebra satisfying these three conditions. So for the nice C-star algebra, we can explicitly describe the A and its dual algebra from the K-theoretic viewpoint. So let's take A as a nice C-star algebra. Then, as mentioned before, this can be understood as a kind of CW complex, which means can be built from some elementary C-star algebras. The building blocks is a trivial C-star algebra and suspension, and the Kunta. Sorry, I forgot to say something about Kunta algebra, but this is a kind of non-commutative analog of Moore space. Moore space is some basic CW complex characterized by its fundamental group, which is cyclic group. And this N means K groups of the Kunz algebra ON is a cyclic group of order N minus 1. So anyway, this Kunz algebra is also very standard C-star algebra, corresponds to some kind of Moore space.
This Mn is Moore space and not the matrices. Mn is not the matrices.
Yeah. So Mn is a Moore space of. Yeah. This is a. And the final building blocks is a tensor product of suspension and the Kunz algebra. So nice C-star algebra can be understood as a direct product of these elementary C-star algebra. So now you can easily imagine that the Spanier-Whitehead duality is compatible with the operation to take the direct product. So we have explicit description of the dual algebra, the trivial system algebra, and the suspension is standard to be self-dual. And the dual of the Kuntz algebra, by using UCT, it is easy to check that the dual of the Kuntz algebra is a suspension of the Kuntz algebra. And the duality, if we take a dual of dual, then this is equivalent to the original algebra. So the dual of this algebra is again the Kuntz algebra. So now we can easily understand A and its dual from the K-theoretic sense. So this is a rough explanation to understand the duality. So next, I'd like to give more precise definition of the duality using the units and co-unit. So this definition is probably, I read the paper of Kaminka, Patnam, and Shoket or Khan. So this, I follow their definitions. Duality classes means a pair of unit and co-units. So let me give the definition of the Spanier-Whitehead duality. So the sister algebra A and BA, they are called Spanier-Whitehead dual. And only if there exists a unit and co-unit. The unit is a map from trivial C-star algebra to the tensor product of A and dual algebra, the DA. And this diagram doesn't mean this is a star homomorphism, but this means the unit is an element of the following KK group. And the co-unit is a map from the tensor product of A and A to trivial C-star algebra. And they satisfy so-called unit-co-unit adjunction formula. So let me explain this unit-co-unit adjunction formula briefly. So by using kind of string diagram like this, one can understand the unit-co-unit adjunction formula as something like a braiding rule. So we consider the following morphisms. The unit, this is a morphism from C to this tensor product algebra. And then we tensor with some identity morphism. Then the resulting morphism is a morphism from A to this triple tensor product. That lives in the KK group. And also, we have another morphism from this triple tensor product to A given by something like this. We use a counit. And then counit is a map from this tensor product to trivial C-star algebra. And by tensoring the identity, we obtain the element here. And as I mentioned before, KK groups can be understood as homomorphisms. So we can take a composition. And the resulting map is a morphism from A to A. And the unit-counit adjunction formula says this composition is equal to identity. So in some sense, this equation can be understood as a following grading rule. So this is a very categorical subject, and the Spanier-Whitehead duality is actually very homological and categorical things. So now, using this picture, I'd like to explain some equation of the KK groups, which I write here. So now, by using this unit and counit, we can obtain, we start from some morphism from A to B multiplied X. We can obtain another morphism from dual algebra of B and dual algebra of A. So the morphism is given by following procedure. So first, we compose the counit for B from right hand side and the unit for A from left hand side. Then resulting morphism is a map from dual of B, and the range is a dual of A. This procedure gives a map from this KK group to this one, and using the unit-counit adjunction, this is found to be isomorphisms. So now, the Spanier-Whitehead duality is turned out to behave as something like contravariant factor, because for given morphism or diagrams, the duality gives a diagram, another diagram with opposite direction. So more precisely, so this notation is not so good because this d is not a factor. So the choice of dx completely depends on the choice of this unit or counit. But anyway, the Spanier-Whitehead duality can be understood as something like this.
So you mean there is no, I mean, if you think of A and B as functors,
Yeah.
mu and nu do induce natural transformations of the functor tensoring with A. Yeah.
Yeah.
Okay, but they're not. So you're saying that they're not functorial, not even
Yeah.
a category,
Yeah.
it's a category of nice algebras. Okay.
So because actually we can have various choice of new A or new B, and the choice depends on the.
But if I mean, I can see that if you start with using an isomorphism between A and this sum of Kunz algebras and so on, then it will depend on that isomorphism. I mean, you know, one way would be, I know my algebra is isomorphic in a non-canonical way to a Kunz algebra. Then the dual, I don't use the dual of the Kunz algebra, and then this will depend on the choice of the isomorphism. But is that essentially what's happening, the non-naturality, or is there another reason? Because for ON, it's natural, isn't it? If the algebra is ON, is there some naturality to the usual choice of mu and nu?
I think no, because
I mean, the formulas, the Kaminker-Putnam formulas they are given by a canonical formula, right? It doesn't depend on choices.
so I see. So you say the I see. So also one of the paper of Kamika and Putnam discussed how to take a unit or a counit from some extension of C-star algebras. And in this paper, their construction is very canonical. But but in general, so for example, this dual algebra, this algebra can be can be determined. This algebra can be determined only up to KK equivalence. If we take another algebra which is KK equivalent to this DB, then there is another unit and counit. So this is a naturality which I'd like to say. So can I answer your question?
No, okay, I'm fine.
Yeah, okay, sorry.
So.
So probably the time is already. So,
it's my fault.
Yeah, nothing. So then so I'd like to go to the homotopy computation of the homotopy groups of the automorphism group of Kirchberg algebra. So probably people now the audience might we get used to the notion KK groups, and I hope you may imagine the following computation. So let's consider the zeroth fundamental group of the automorphism group. So this thing is a kind of set of homotopy class of the automorphism group, and the automorphism group is some bijective isomorphism, bijective homomorphisms between A and A. So this object is something like the set of homotopy class of hom AA. Strictly speaking, this is completely wrong, but the feeling
homomorphisms are not isons, right?
And as I said before, KK groups is exactly compute this object. So I hope this explains the feelings of why we can compute the kind of homotopy group by using the KK groups. And there are many formula to compute such homotopy groups. Today, I'd like to use one given by Marius Dadarat. And he gives a formula for the unital Kirchberg algebra. Let A be a unital Kirchberg algebra. So I say nothing about the Kirchberg algebra, but Kirchberg algebra is some kind of nice C-star algebra, which is very important in the classification theory of C-star algebra. And then this homotopy group of automorphism group is equal to the following KK group. Yeah, we put I, but this is also some KK group. So let me explain about this CUA. This is called the mapping cone C-star algebra associated to the position of the unit of A. So let me explain about mapping cone algebra. If A is a unital C-star algebra, there is a canonical map from C to A. And then we can extend this sequence to kind of exact sequence. This is not exactly exact sequence in the sense of the ring theory, but in some sense, for example, in some triangulated category sense, this is actually kind of exact sequence. So this is a mapping cone C-star algebra, and this has a following explicit description. So as I mentioned, this is a kind of exact sequence, and indeed, this induces a long exact sequence of K group. Yeah.
Okay, so sorry, UA is the map from C to A.
Yeah.
Yeah, because you know, when you first wrote QA, I thought Kunz, CU.
This
That CU might come from Kunz, but it doesn't. Yeah.
Yeah. Yeah, actually, this symbol also can be understood something like this, but yeah, this is UA. So yeah, anyway, then G is a K0 group of C, and this one is just equal 1 here. And then this one is mapped to some element which determines the position of the unit of A. And then this sequence continues something like this. So now we can easily check the following remarks. We know the group of A and the position of the unit. Then, by using this exact sequence, we can compute the K group of mapping form. And also K group of A itself. This is always okay, but in general, the compass direction is not true. This is not true in general, even if the C-star algebra is a don't C-star, even if the case of the K group of A is a kind of infinite direct product of Z, this compass direction doesn't hold. But anyway, if A, the K groups of A is finitely generated, we can also check this compass direction. So this is one of the place where the finitely generatedness plays a crucial role. So, so let's go back to the computation of the homotopy groups. Okay.
Okay.
So now, so we consider the nice unital Kirchberg algebra. Then, thanks to the Landalas formula given by the KK groups, and if A is a nice C-star algebra, the nice property completely inherits to the mapping con algebra. So mapping con algebra is also nice C-star algebra. Then we can take a Spanier-Whitehead duality. And this is exactly equal to the ice K group of this tensor product algebra. So now the homotopy group can be completely described by the K group of this algebra.
Okay.
Okay. So now I'd like to propose the following abstract question. So that is, when given two nice unital Kirchberg algebra share the same homotopy group, so the answer is the reciprocality, which I said which I'd like to explain this talk. But before proceeding to the reciprocality, I'd like to explain the motivation of why I ask such a question. So motivation comes from my previous work on the bundles of Kunz algebra. So as I said before, this is a very standard object in the C-star algebra theory, which corresponds to kind of non-commutative analog of Lua space. And there are several research investigating some nice invariant to classify the bundles of Kunz algebras. And Marius Dadarat finds some nice invariant using the topological K theory of the base space X. And his results is actually difficult. He used some very many technical tools. On the other hand, there is another bundle of unital Kirchberg algebra, which is a kind of matrix algebra. So here, O infinity means some nice Kirchberg algebra, which is KK equivalent to trivial C-star algebra. So roughly speaking, this is a bundles of matrix algebra. So the classification of such bundles is actually easy. And in my previous work, I construct the natural bijection between these two sets. So I think this bijection is interesting, and I wonder why these two unital Kirchberg algebra have such nice property. And important property of these two Kirchberg algebra is that they have the same homotopy group of the automorphism group. So this is a motivation to ask such an abstract question. So in the introduction, I said the homotopy equivalence is something like this, but we need a morphism between this space, these two spaces. But in this case, I think that is also interesting, but I don't know why. But so there is no hope to construct some nice map between these two groups because these two Kirchberg algebra is completely different. But anyway, so this is a motivation to ask such a question. So probably in the rest of 5 or some minutes, I'd like to explain the definition of the reciprocality, which explain this question. Sorry. Now, by the above argument, this equivalence relation is equivalent to the following KK equivalence. And this is one relation with two variables. So you may wonder there should be infinitely many solutions to this equation. But surprisingly, there is only non-trivial solution. The trivial solution is that this is actually trivial. This is a case when A and B are actually isomorphic. And the non-trivial solution, this is a definition of the reciprocality, which says the dual of the mapping of A is equivalent to B. This is equivalent to B, and A is equivalent to the dual of mapping of B.
So when you say isomorphic, there you are using that A and B are Kirchberg algebras, and thus KK isomorphic is the same as C star algebra isomorphic.
Yeah, this means C star algebra isomorphic.
Yeah, but there is where you're using that for Kirchberg algebras is the same.
Yeah, yeah. So, yeah. So this is a definition of the reciprocal, and so so let me give some 4 remarks on the reciprocality. The first, reciprocality is not so weak phenomena because for every nice unital Kirchberg algebra, as I said before, the nice unital Kirchberg algebra contains, in some sense, the class of finite CW complex. So there are many targets to apply the reciprocality. Then you use this another C star unital nice Kirchberg algebra B. This is a dual which is reciprocal to A. The second, the reciprocal algebras are automatically not KK equivalent. So they are completely different Kirchberg algebras. And also, so I like to mention this thing. The reciprocality is different to the duality. Anyway, so but the next third remark explains the relationship between the reciprocality and the duality. So let's consider the mapping cone of unital C star algebra A. Then, as I said before, the Spanier-Whitehead, this is a duality. Duality behaves something like contravariant factor. So provides another diagram with opposite direction. And trivial C star algebra is self-dual. And by using the UCT, we can find unique unital Kirchberg algebra B here and the KK equivalence here, which makes the diagonal commutes. And also, the mapping cone algebra of B is automatically equivalent to dual of A, and we can make a commute here. So this is how reciprocal algebra are related via the Spanier-Whitehead duality. And last remark. So implies. Last remark gives one understanding of the reciprocality. So let's consider the sorry, I have actually 5 remarks. The fourth remark, if the unit of A is in the torsion part of the K0 group, then this automatically implies the unit of B is automatically non-torsion element. So using this picture, we can obtain an understanding of the reciprocality as follows. So let's consider the class of nice Kirchberg algebras. Then a nice unital Kirchberg algebras. Then this is divided into the following 2 subclasses. One is a class of A, whose unit is a torsion element. For example, the Kuntz algebra sits in here. And another one is a class of B, whose element is non-torsion, whose unit element is non-torsion element. And matrix algebra is in here. And the reciprocality gives a one-to-one correspondence between these 2 subclasses. And I'd like to finish here, but finally, I say just one thing. So this reciprocality also implies the natural bijection between the bundles of A and that of B. Which is proved by showing the Spanier-Whitehead duality for the category KKX. And this is a most important result on the reciprocality. So I'd like to stop here. Thank you for your attention.
Thank you very much, Taro. I already pestered you with lots of questions. So does anyone else have a question apart from me? Let's give someone else the opportunity.
Thank you.
Let's see. I don't see any raised hands. Yeah. So I have one more question. So
yeah,
by your diagram here, the reciprocal of ON is Mn minus 1 or infinity, right?
Yeah. So
and what happens with the suspension?
What's happened with the suspension? So
I mean, what happens with, so if I take a Katsura algebra, what do I get on the other side?
So I think the Katsura algebra is something like a, it seems to be more closer to the duality. So
but I mean, it's a Kirchberg algebra, right?
Yeah.
So it might be in one of the 2 families, and depending on the matrices, right? So is there, does it correspond?
So you mean
No, no, to me, that would be the dual, not, not the reciprocal,
yeah.
which I understand are different. So somebody has a question in the chat, but I don't know if it's addressed to you or to me, because because it's about algebra KK, and I don't know. I am the expert in algebra KK. I don't know the answer to that.
Where y is a finite theta from there. An analog of this for algebraic KK. Also, there's a proof of this entail equivalent criteria that describe the bootstrap category of system. Proof of this entail.
So it's the bootstrap category that the thick triangulated category is generated by the complex numbers, right?
Yeah.
No? So that's, so you're saying that that's the same as the category of complexes, of finite complexes.
Yeah. So I think the finitely generatedness is very essential in this talk. So first of all, the Spanier-Whitehead dual, it can be exist, but it cannot be realized by some separable C-star algebra if the K groups of original algebra is not finitely generated. This comes from purely homological reason. So kind of this criteria that say, I think say nothing about for all bootstrap class, because bootstrap class also contains a kind of inductive limit, which is no more something like finitely generated object. And
but if I mean, if in the definition of triangulated category generated by, you just include finite operations, like finitely many directions, finite many modes, and so on.
Yeah, so in this case, so I don't want that. Yeah, sorry, I can't say anything more
Okay.
here. And also, yeah, thank you very much for your question. I'm sorry, I know a little bit about some algebraic K or something.
Okay. Well, it's been a pleasure. You know, this thing with the Katsura algebras, I have been thinking about this, so I thought it might be interesting to bounce it back and forth with you to see, you know,
yeah,
some ideas pop up. Okay, so thank you for the wonderful talk.
Thank you.
We'll see. So you're welcome. I know it's 12 hours difference, right? With Tokyo. So But if you ever have the opportunity, you're welcome to attend our seminar in the future.
Yeah, thank you very much.
Okay. So I stop the recording now.